Chapter 6, Determinants, finally. In pre-calculus, this is such a prominent chapter, something we talk about a lot, and in linear algebra it had to wait until chapter 6 to be really addressed. Why is that? Well, determinants are great, they're very useful, very powerful, but the philosophy of many college textbooks is that determinants kind of undercut some of the understanding that we can have of concepts. For example, you know that a matrix is invertible if the determinant is not 0. Well, that's great to know, but it doesn't really explain much. And so what we've tried to do in linear algebra is show that a matrix represents a linear transformation, and if the matrix is invertible, it means the linear transformation is invertible. Now we can think of the column vectors of the matrix. They are the image of the basis vector, and we want all of these basis vectors, or the image of these basis vectors, to be linearly independent. If they're linearly dependent, well, we kind of lose a dimension. We have a collapse of one dimension, and then it's not going to be invertible. So many things we see in this chapter now in the notes are going to be a little bit review or stuff that you may have even learned somewhere else than in pre-calculus. So firstly, a reminder, the determinant of a 2 by 2 matrix is given by AD minus BC, and the inverse of a 2 by 2 matrix, this is the only thing we actually have done in linear algebra before, is given by this formula here. One note, even though it's not the case with our textbook, oftentimes determinant of A is written with like these absolute value symbol. And so the goal that we want to have for determinants is we want the determinant to be a number that is such that if it's 0, the matrix is not invertible, and if the determinant is not 0, then the matrix is invertible. So the determinant is like a signature a little bit. You can have a huge matrix, a 100 by 100 matrix with 10,000 entries, and actually the determinant is just one number. It's one number that characterizes the matrix in some way. So how are we going to get to this goal, to find a number, to find a way to express a number from a matrix such that if it's not 0, A is invertible? Well, for 3 by 3 matrices, we are going to use what we saw in multivariable, which is the triple scalar product. If a matrix is given by its column vectors, U, V, W, we saw that the triple scalar product gives the volume that is generated by these 3 vectors. So the triple scalar product is given here, and we can just define, so we can just decide, okay, the determinant of A is going to be U dot V cross W. So let's see what this is if we expand. So U is A11, A21, A31, V is A12, A22, A32, etc. If we expand, this is what we get in the end, this long expression with 6 terms. So that's what we're going to pick for the determinant because it fits our goal. Now there's a rule that I don't think we really teach in pre-calculus, but you've seen maybe before. It helps us find determinants of 3 by 3 matrices a little bit faster. So what you do is, if you have a matrix, you just repeat the first and the second column, and then you look at diagonals. Every diagonal that goes down towards the left will have a minus sign. So here it's A13 times A22 times A31 with a negative sign. And then another negative sign minus A11, A23, A32, minus again. And then for the 3 diagonals that go down towards the right, we have a positive sign. And if you compare this with the previous page, you'll see it's the same 6 terms. So the example here uses Sarus rule for what values of a matrix, for what values of lambda is a given matrix invertible. we want this to be not 0, we just use Sarah's rule and we get that the determinant of A is lambda times lambda square minus 1. So A is invertible for lambda not equal to -1, 0, 1. The general case for n by n matrices is called Laplace expansion, and we're not proving it. You can find more in the textbook if you're interested. So Laplace expansion is something that we're going to describe with examples. You also learned that in pre-calculus how to find the determinant. You have to pick a row or a column, and the best row or column is usually the one that has the most zeros, because we're going to be multiplying. And then you have to remember, if here I pick the first column, that there's a sign attached to each entry in the matrix. It's plus, minus, plus. There's always a plus at the top left, and then it would be -2 if I were to pick the second column, minus, plus, minus. So it always switches between minus and plus if you move horizontally or vertically. And then you just use this 4 and you multiply by the smaller matrix if you remove the row and column that 4 is in. So here it's 4 times the determinant of -1, 2, 1, -2. And then -3, and again times the determinant of the smaller matrix if you remove this row and column. And so it's 2, 2, 1, -2 here, and then +1 again. All right, anyway, you get 21, and you probably remember that from pre-calc. So this is a way to generalize that can be used for any size matrix, and it has the property that we wanted, that we wished, that if the determinant of A is not 0, then A is invertible, and vice versa. So in this example here, we can see how one of the good choices is to pick the last row, because it has 2 zeros, so we're basically going to have 2 of these terms vanishing. So plus, minus, plus, minus, plus, minus, plus, and then you can just proceed to developing, and you're going to have to do that twice, of course, because this is -5 times the determinant of a 3 by 3 matrix, which will require us to go one step further. And here I picked the first column, but apparently we could have picked the third column, and it would have been even a little bit faster since there are 2 zeros in the third column. One special case that's very quick is when we have triangular matrices. Here, so it's a upper triangular matrix. There's zeros everywhere below the diagonal. If you pick the first column, you're going to have 5 times this 4 by 4 matrix. And the determinant of that, if we pick the first column of this smaller matrix, is going to be 2 times this 3 by 3 matrix, which is going to be 1 times this 2 by 2 matrix, which is going to be -2 times 4 minus 0 if you do AD minus BC. So what we notice here is that for upper triangular matrices or lower triangular matrices, the determinant is simply the product of the entries on the diagonal. So that's the theorem that's below that I added here by hand. The determinant of a triangular matrix is the product of the diagonal entries. For the exercise itself, we get -80. Okay, I just added a part that was missing, and this is the last bit for this chapter. The volume of a parallelepiped generated by some vectors is given by the square root of the determinant of the transpose of A times A. So volume is just a general term here. It means area if it's just 2 vectors, or more than just a 3D volume if we have more than 3 vectors. In the special case that we have m vectors in Rn, then the volume can be simplified, and it's simply the determinant of A. So in here, the example is 2 vectors in 3D. So you see how you couldn't just take the determinant of A, because matrix A would be 1, 2, 3, -2, 0, 4. It's not a square matrix. We can't take the determinant. But we can take the determinant of AT times A and the square root, and that gives us the volume or the area, but really we can just say the volume of this parallelogram, volume between quotation marks. So that's it for chapter 6. Thank you.